Okay, Greg, thanks so much. I really enjoy coming back to Fort Collins. A lot of formative years here. I feel like I became a man here. Fort Collins taught me a lot of really important lessons, and it still has that wonderful charm that it always had. I'm very lucky to live here. I think it's a beautiful, beautiful place to live. So, the most important thing, particularly for your graduate students to think about, and this is really what I want to focus on today in sort of an abstract way, is it's all really about the environment. And what I want to talk about today is how we interact with the outside world that is defined as a mucosa. So mucosa is any tissue that is lined by an epithelium that somehow communicates with the outside world. And this establishes in any organism a really important microenvironment. And it's understanding those microenvironments that become important to understanding both health and disease. And this is what I want to really talk about today, is what are these environments, how are they established, and what are some examples of really dramatic environments. So the dramatic environment I want to talk about today is the gut. And it really is, I think you'll appreciate at the end of this talk, some of the conceptual ideas that this is a really austere, quite austere environment that this microbiota lives in. Okay? So I don't need to belabor the point that the intestinal microbiota is, at a minimum, a complex environment. At probably, we just don't understand what's going on at all, I would say. Right now, it's really in its infancy of understanding. There are some things that we know. I think you've heard this mentioned already. There are approximately 10 to the, at least the estimate is 10 to the 14 organisms. Most of those exist in the colon. The population increases as you go from the top to the bottom. 10 times more cells than in the eukaryotic organism, and 100 or 1,000 times more genetic material. Kareem mentioned this yesterday, that there's approximately 1,000 times more DNA in that microbiota relative to the eukaryotic organism. It was mentioned this morning that the microbiota is acquired at birth. There are approximately, I'm not sure what the most recent estimate is, about 1,000 species that are represented. That's at least as best as we can estimate. And are very, very diverse metabolic abilities of this microbiota. So this is something that we'll touch on. And then also, really importantly, this is really what drives this microenvironment, is the metabolism that is ensued by this microbiota that endows this microbiota to interact with the host at a very basic level. Okay? So I think one of the funny things, one of the more interesting things today is that we really consider this, the microbiome, and this is, I think, really how we have to start thinking about this. This is a new organ. This is a recently discovered organ that we have to think about as a prokaryotic organ living in a eukaryotic organ. Okay? So as a starting point, this was actually, I think, mentioned yesterday. I think Kareem mentioned this yesterday too. One of the big things that you see here in the disease. So the disease that we're going to talk about today is the colon, and specifically we're going to talk about the inflamed colon. What happens when that organ becomes inflamed? One of the things that's now appreciated is that there are very selective depletions of specific microorganisms during ongoing inflammatory disease. Okay? And one of the better characterized now is the selective depletion of butyrate-producing organisms. Okay? Butyrate is one of the short-chain fatty acids. It's made through fermentation by anaerobic bacteria in the colon. So, short-chain fatty acids, they are primarily come in three flavors: acetic acid, propionic acid, and butyric acid. They exist, so as I said, they are microbial fermentation products. They exist at, that's not a typo, 130 millimolar concentrations in the colon. So you can't imagine anything that lives at a higher concentration than short-chain fatty acid. So 130 millimolar concentrations in the colon. This applies overall about 6 to 10% of overall energy for the organism, okay? And that's overall energy. In the gut, about 40% of all energy for the lining epithelium comes from primarily butyric acid, butyrate. And it has very pleiotropic functions. We'll talk about this in a second, but it's a histone deacetylase inhibitor, and it also has functions where it can, the short-chain fatty acids can bind to surface receptors and signal to various components, various cells within these mucosa. So, how is it that butyrate functions as a short-chain fatty acid? So this is something that's recently appreciated now to be very, very important. Okay? Why? So take a step back and look at this, right? If butyrate becomes depleted, and it's the primary energy source for the lining epithelial cells of the gut, what happens when that tissue becomes inflamed, right? It needs another energy source, and it likely becomes much more susceptible to damage, much less likely to heal under these circumstances. So it's now recently appreciated how this actually works. So butyrate is made by the mucosa, it's made by the microbiota, the lumen of the gut. It's transported through two very specific transporters into the cell. Once inside the cell, butyrate is immediately converted to acetyl-CoA, where it then can essentially burn in mitochondria as a primary energy source. Okay? But more importantly, butyrate decreases the ability of these cells to use glucose as an energy source. And the way it does this is through the inhibition of HDAC, so it's an HDAC inhibitor, and this drives the expression of pyruvate dehydrogenase kinase. The expression of PDK inhibits the conversion of pyruvate to acetyl-CoA, so it cannot, under those circumstances, utilize glucose as an energy source. Okay? So again, take a step back and look at that. If the primary energy source for these cells becomes depleted during inflammation, this makes the tissue very susceptible to damage. Okay? So, we've modeled this. So we recently did a very, very simple experiment. We took a mouse model of colitis, the DSS colitis model. This has been mentioned a couple of times. It's essentially just an epithelial irritant that causes a disease very similar to what we see in humans called ulcerative colitis. And we tried to recapitulate these observations that we've seen in human disease. So we asked the question, do murine models replicate this disease? And if so, is it really relevant to disease? Okay, so here was the experiment. We took C57 black sex mice, so just wild-type black sex mice, and exposed them to DSS colitis for 7 days. We then measured short-chain fatty acids and correlated these with various aspects of disease. So we looked at, for example, intestinal permeability, we looked at clinical endpoints of disease, tissue cytokines, and we found some very interesting things. So first, very surprising to us, this was an experiment that really I don't think had ever been done, very surprising to us is by screening or by profiling each of those short-chain fatty acids. Shown in red are vehicle-treated animals, and the colitic animals are shown in blue. And you can see here that by looking at acetic acid, propionic acid, butyric acid, and overall short-chain fatty acids, butyrate was very selective. Okay? Even total short-chain fatty acids were not statistically significant, but very prominently, butyrate was selective. So this gave us then the opportunity to correlate this with some of the features. So one of the clinical endpoints we use when we study mouse models is just loss of body weight. So how much weight do these animals lose? And you can see here that these animals lose up to, even very sick animals, 15% of their body weight in 7 days. But you can also see here, very nicely, that if you look at the cecal butyrate concentrations, you correlate this with the decrease in body weight. So decreased butyrate levels are associated with increased weight. Okay? Other aspects, chemokines and cytokines. So this turned out to be pretty interesting, and it looks like we still don't really understand, but it looks to be something interesting. So first, KC, which is the, for those of you in the chemokine field, you know that this is the IL-8 homolog in mice, correlated very nicely with cecal butyrate. Again, low butyrate levels and high KC levels, so pro-inflammatory, and also with IL-6. Again, a negative correlation with cecal butyrate. So this seemed to be somewhat specific since IL-12 P70 and gamma interferon did not correlate under these circumstances. And then finally, looking at permeability. So this is something that Kareem talked about yesterday. Intestinal permeability correlates very strongly with disease outcomes in inflammatory bowel disease. So intestinal permeability was significantly increased with TSS colitis, and then again negatively correlated with cecal butyrate levels. Okay, so a very strong association between low butyrate levels and illness under these circumstances. So let's take a look at the microenvironment. Okay, these are histologic images. On the left is a healthy colon, and the right is ulcerative colitis. So I know a lot of you don't look at histology, but two things that you want to really look at are the amount of cellularity in a healthy tissue versus that in ulcerative colitis, the number of cells that are inside. So essentially, we're looking at a single epithelial layer lining the entire GI tract from stomach down. And what you see here is basically that the outside world would be the inside of these crypts, looking down onto the top of the crypt. You can see this very nicely over here, that this is essentially the outside world. And the things that you see are the cellularity. These are the white blood cells, leukocytes moving into the tissue during ongoing inflammation. And you see that cells, some of these white blood cells have actually even crawled across this single layer of epithelial cells by disrupting that epithelial component, resulting in increased permeability of that tissue. So there are a few things that we've learned over the years about this microenvironment. Number one is during an inflammatory event, there's a significant increase in energy demand to that tissue. So that tissue requires significantly more energy in the process of healing and resolving inflammation. We also know that there's an increased oxygen demand. I'll touch on this in a minute, but the cells that move into this tissue can utilize tremendous amounts of oxygen. And during that process of oxygen utilization, it makes that oxygen not available to the rest of the tissue. We also know that there's diminished blood supply. So the vasculitis, so the inflammation of the vasculature associated with these diseases also decreases blood flow. So a few years ago, we came to appreciate that this probably resulted in some changes to the tissue that included changes to oxygen levels. So we became interested in understanding how oxygen distribution in that tissue and metabolism of oxygen is important for disease processes. Okay? So one of the questions that we ask is, are inflamed tissues actually hypoxic? So is that oxygen metabolism influenced, and are there changes to oxygen distribution? So we ask the question, are they hypoxic? And the answer is definitively yes. So the way we discovered this is we utilized an antibody that's directed against adducts of two nitrobenazole dyes. So the nitrobenozoles, here's a structure of one of these dyes, is essentially taken into a cell, and the reducing nature of the cytoplasm of the cell generates a very reactive nitrogen species. This nitrogen species, in the presence of adequate oxygen concentrations, regenerates itself, is passed out of the cell, and then is essentially secreted in urine. When oxygen levels are low, these adducts can then essentially bind to macromolecules in the cell, and those macromolecules then can be localized with antibodies. Okay, so these were originally discovered by Edith Lord and Cameron Koch at the University of Pennsylvania to image large tumors. The concentric portions of large tumors are quite hypoxic, and the idea was to image these tumors. So we used these for inflammation. And here was the result. So two things came to this. First is looking in the colon. I talked about a very austere microenvironment. Well, one of the things we noticed is that the localization of these dyes at the most luminal surface of the epithelium, of the most luminal portion of the colon, were quite hypoxic. So this is a PO2 of less than 10 millimeters of mercury. Okay? So remember that along this apical surface, along this luminal portion, anaerobes grow. So there is no oxygen there. That means what? That means a very steep oxygen gradient across the luminal portion of these cells. The second thing we noticed, so we termed this physiologic hypoxia, right? In a healthy tissue, physiologic hypoxia. In a colitic animal, you can see here the disruptive architecture that goes much deeper and much more intense along that luminal axis. Okay, so let's touch on this first. So in the colitic animal, how is it that these tissues become so incredibly hypoxic? I'm not going to go into the details. This was a paper that we published a couple of years ago, but I showed you in the histology pictures the white blood cells that migrate into the tissue. Well, as those cells, so that's these cells migrating out of the vasculature and toward these epithelial cells, they utilize oxygen to the extent that the rest of the tissues sense this as essentially a hypoxic incident. Okay? And this triggers the expression or the stabilization of a protein called hypoxia-inducible factor. We'll talk about it in a second. But essentially drives the expression, as a transcription factor, drives the expression of lots of genes important in the resolution response. So this is actually an adaptive or protective response to the tissue. So what about this physiologic hypoxia? So this is where the microbiota comes into play. What's going on this luminal surface that these cells can actually survive at such low oxygen concentrations, and what drives that signal? So we took a couple of graduate students in the lab have really teamed up on this. And what we did is essentially looked at how much of a gradient of staining exists in these tissues. So what you can see here is if you simply take the pyridoxal dyes, so these are the hypoxy-probe dyes, if you look at hypoxia and you plot this, on the vertical axis is the fluorescence intensity with distance from the lumen. And you plot this, you see that this signal falls off very rapidly and very consistently. So this was data from 100 colonic sections. So Caleb Kelly and Leon Zhang are both MD PhD students in the lab, and they proposed what I think at the time was a pretty provocative hypothesis. They proposed that short-chain fatty acids would drive this, based on some signal from the lumen of the gut driving this response. So they proposed that short-chain fatty acids drive this response. So they proposed that short-chain fatty acids actually make cells hypoxic, right? So to monitor this required that we develop a system. So some of you will know this system. So this is essentially the transwell systems. We plate the cells upside down on these inserts to allow physiologic regulation of transport and for cell migration assays. So we plate these essentially on the bottom of the pyramidal support. We then worked with a company in Germany, actually in the brewing industry in Germany, believe it or not, and we developed a system in which we could monitor in real time oxygen concentrations at essentially the surface of the epithelium. So this would be the lumen of the epithelium, with the lumen of the gut. Imagine this. So the SDR system allowed us basically to monitor in real time. So the way this works is these are fluorescent spots, and you essentially have a miniature fluorescent plate reader, which allows you on a 1 second interval to monitor the local oxygen concentration in this microenvironment. So we did this, and lo and behold, we found that butyrate, in a quite significant way, induces epithelial oxygen consumption. So maybe not surprising, it is a fuel source. And you can see here that with the addition of butyrate, a very, very prominent increase in oxygen consumption by these cells compared to their controls. This is relatively specific. It did not occur with propionate or acetate, and most surprisingly was the activation of this transcription factor. So hypoxia-inducible factor was activated in a very prominent way, in a dose-dependent way, with the addition of butyrate. So, what is HIF? HIF is, as I said, a transcription factor that was originally discovered based on its ability to regulate oxygen-dependent genes. The first gene that was demonstrated to regulate is erythropoietin. So when you become hypoxic, what do you need? You need red blood cells. You need a hormone that makes red blood cells. It was discovered originally based on its ability to regulate EPO. There are now probably 200 genes that have been shown to be regulated by HIF. It has this very interesting post-translational modification, which is hydroxylated by one of three prolohydroxylases. It's hydroxylated in two areas, where when hydroxylated, it's targeted to proteasomal degradation. It's basically targeted for its degradation. When oxygen becomes limiting, the hydroxylation reactions are inhibited. This allows the expression of the alpha and the beta subunit in the nucleus, where it then drives transcription of specific genes. Okay, so low PO2, stabilization of HIF, activation of transcription. So over the years, it's been demonstrated that HIF1, and specifically there is a HIF2, but HIF1 is quite protective in a number of mucosal inflammatory models. So the knockout of HIF1 alpha has been shown to increase susceptibility to disease. The overexpression of HIF1 is protective, and now there is the development of inhibitors of these PHDs. So the PHD inhibitors stabilize HIF. The development of these molecules has been shown to be protective in a number of different disease models. The primary target for this disease, for these PHD inhibitors right now, is renal anemia, because it's essentially a GP level. So you can drive expression of erythropoietin using performance collagen substance. Okay, so let's come back to these models. So let's come back to this physiologic hypoxia. And so we did two things. One is, if you treat animals with antibiotics, first thing you see is within 24 hours, essentially unmeasurable levels of butyrate. This results in the loss of this hypoxyprobe staining. So this appeared to confirm what Caleb and Leon had proposed, in that short-chain fatty acids is correlated very strongly with the loss of this physiologic hypoxia. And then secondly, that HIF1 alpha, so the stabilization of HIF by butyrate, appears to also correlate with the loss of butyrate. So treating animals with antibiotics or doing this is essentially a HIF reporter mouse. You see here the loss of HIF signaling in animals treated with antibiotics. The other obvious question then is germ-free mice. So, right? So we have established a colony of germ-free mice in Denver. And what you can see here is that if you stain for hypoxyprobe, believe it or not, there is an antibody on here, but you see essentially no hypoxyprobe staining in the germ-free. Whereas here is your colonized animal. And likewise, germ-free animals express less HIF than their conventional counterparts. So, a very strong support of that hypothesis. So, let's talk a little bit about barrier function. So, barrier function is regulated by butyrate. This has been shown previously. The question is, how does this occur? So, in this case, what we did is we used again the transwell system, and we exposed those transwell systems. We exposed the cells plated on these transwell systems to butyrate, propionate, or acetate. And you can see here that butyrate very nicely enhances both barrier and the rate of formation of barrier under these circumstances. Okay, so short-chain fatty acids appear to promote the formation of barrier function from plated cells. So one of the observations that we made a couple of years ago, this very similar response suggested that this was correlated with the expression of the IL-10 receptor. So IL-10 is an anti-inflammatory cytokine, which people think that it's a regulatory cytokine, important in the healing process, important in health. So it's expressed on the apical surface of epithelial cells, and it's the lack of the IL-10 receptor impairs barrier function, and also it's important to note that human beings that lack the IL-10 receptor get colitis. This is one of the things, a very severe form of colitis. So we propose the idea that butyrate might regulate barrier through the expression of the IL-10 receptor. And lo and behold, that does appear to be the case. So here are two cell lines, so KCO2 cells and T84 cells. You can see here that increasing concentrations of butyrate increase the expression of the IL-10 receptor. Likewise, in promoter assays, so it appears to be a transcriptional response. So butyrate drives the expression of the IL-10 receptor promoter and also signaling through SOX3. So several different layers of evidence there suggest that the IL-10 receptor is probably regulated directly by butyrate. Loss and gain of function. So the additional experiment that Leon did was he knocked down the IL-10 receptor, or he overexpressed the IL-10 receptor in panels A and B respectively. And you can see here that this correlated very strongly with the formation of barrier. So the loss of the IL-10 receptor resulted in diminished kinetics for the formation of barrier, and overexpression of the IL-10 receptor enhanced formation of barrier from platelet cells. Okay, so the last piece of evidence then was to look at the IL-10 receptor in antibiotic-treated animals and in germ-free mice. So in the top two panels, you're looking at colon and ileal IL-10 receptor in the presence and absence of antibiotics. And you can see here that the IL-10 receptor is decreased in antibiotic-treated animals. If you also take germ-free animals and conventionalize them over a 30-week period, you can see here a nice correlation of increased IL-10 increased IL-10 expression as animals conventionalized from germ-free. So the other thing we have to talk about when we talk about barrier is the components of the membrane components that actually form that O-ring that forms barrier. So there really are sort of three areas, three levels of expression. So the tight junction is the primary O-ring for the cell. This is really what provides a selective sealing of us to the outside world. And it's composed of numerous proteins, claudins, gins, and occludins. The second level is the adherence junction, which is primarily adherens and catenins, and then gap junctions at the bottom are for cell-cell communication. So one of the components of this that we have looked at are the claudins. So not to get too deep in the weeds on this, but there are 27 claudins. It's a large family of proteins, 4 transmembrane helice proteins. What's important to know is that there are leaky claudins and there are tight claudins. So some claudins expressed there make the monolayers tighter, and some make them looser. So it's important to know that claudin 2 is the primary leaky claudin, whereas other claudins are the formation of the tight claudins. So what we did is we profiled the influence of butyrate on the various claudins. And you can see here that in KCO2 cells and T84 cells, which form very tight monolayers, the commonality really was the loss of claudin 2. So claudin 2 is a leaky claudin, so the loss of the leaky claudin leads to a tight claudin. And this is the proposed hypothesis. So you can see here that in T84 cells, in KCO cells, the loss of claudin 2 correlates very strongly with butyrate regulation. You can see this here by Western blot. So increasing concentrations of butyrate result in the loss of claudin 2. If you overexpress the IL-10 receptor, which correlates with butyrate production, you see a loss of butyrate. If you knock down the IL-10 receptor, you see the overexpression of claudin 2. So it looks like the butyrate IL-10 axis likely regulates claudin 2 expression. So just to summarize this portion, the gut microbiota, through its fermentation process, it generates literally tens of millimolar concentrations of butyrate in the lumen of the gut. Taken into a cell, drives the oxygen concentrations to the point that HIF is stabilized. HIF is stabilized, then promoting the regulation, the transcriptional regulation of genes found in the tight junction. This is a very important aspect of wound healing and resolution of inflammatory disease. And likely it's important for physiologic function of the mucosa. Okay, so let me touch base on the most recent work in the lab, all of which is unpublished. Erica Alexiev and Jordy Lanis are both postdocs in the lab, and they have proposed that host and microbial-derived metabolites shift the balance during inflammatory diseases. So one is taking on the host side, or the host microbial side, or the host side of the host microbial aspect. One is taking the microbial side. So here, so this hypothesis was based on a tissue metabolomics profiling we did. So again, a very simple experiment. We took lytic animals and we took control animals, and we did overall profiling of colonic tissue and serum, and just measured 1,200 metabolites. And you can see here just a principal component analysis, a very nice separation between the two. There's 6 animals in each group, and it allowed us the opportunity then to begin to probe metabolites and their role in active inflammation. So this is a random forest plot. Random forest plot, I sort of look at it as the forest from the trees. Here's the forest, now we're starting to look at the trees. So the higher up to the right-hand corner you go, the more important this is, relatively so, to the overall phenotype that we see in the animals. And I won't belabor the point, it's just a list, but I will point out that there was something that came out of this. So 2 of the top 20 metabolites that came up were important in tryptophan metabolism. And the reason this is important is, and interesting, is that this is a host. So kynurenine is actually a host-derived metabolite of tryptophan, and indoles are microbial-derived tryptophan metabolites. Okay? So you can see here that if you look at the top 2 of this heat map, that tryptophan and particularly kynurenine and kynurenate increase in the serum and in the colon of mice with colitis. So this is, again, serum and colon. So you can see here that tryptophan goes really kind of in 2 directions during inflammation. It can be converted to kynurenine, or it can be ultimately converted to serotonin by the host. So this work, Jordy actually has this now in press, and she has demonstrated that tryptophan metabolites activate endogenous aryl hydrocarbon receptors in the cells and drive the resolution response of inflammation through this pathway. So this is all really kynurenine based. This paper is now in the press. How about the microbial side? So if we look more at the microbial side, we can see here that tryptophan is metabolized to indole or indole derivatives. So several different indole derivatives come out of this tryptophan metabolism pathway. So you can see here, so we developed an HPLC assay for screening these compounds. So in one sweep of the HPLC, we can see at least 3 of these indole metabolites. So this is indole aldehyde, indole propionate, and indole itself. And you can see here that with colitis, so with active inflammation, all of these molecules appear to decrease. You can quantify this here. Indole aldehyde, indole propionate, and then indole itself essentially goes away. Now, interestingly, what Erica did is took serum from ulcerative colitis patients and demonstrated that indole propionate, very specifically indole propionate, is decreased by about 60% in patients with active ulcerative colitis. As those patients then go into remission, those same patients with remission, indole propionate levels come back. So it appears to be a reasonably good biomarker for active intestinal inflammation. Far removed, so this is a serum sample, so far removed from the tissue. So again, what Erica demonstrated, very interestingly, very similar to what we had seen before with butyrate, is that indole propionate drives the IL-10 receptor. You can see here by message, by protein, and then by taking intestinal organoids, so these are primary epithelial cells. They're oftentimes criticized by using cancer cell lines, so we're now using organoids and interoids, and you can see very nicely here that with addition of indole propionate, a very prominent induction of the IL-10 receptor. So again, it appears that this microbial host crosstalk pathway exists at the level of indole regulating the IL-10 receptor. So we've taken this one step further. So tryptophan The tryptophanase is the primary enzyme made by bacteria. There are about 85 species that are indole positive bacteria, about 85 species that make tryptophanase, and the end results are indole, pyruvate, and ammonia. So one of the things that Erica has recently done is made an E. coli, a tryptophanase mutant of E. coli. And you can see here, this is just some of you may know the Kovacs reagent. The Kovacs reagent is essentially detects indole. And you can see here that wild type E. coli, this is a tryptophanase mutant, not making indoles. And then here's a tryptophan transporter mutant that still is indole positive. And you can see very nicely here on this HPLC tracing that there is essentially no indole made by these mutants. So we've done a couple of things with them. So first, we've taken supernatants from these E. coli and just diluted that supernatant and looked at the IL-10 receptors. So here's a Western blot. This is your wild type E. coli. You can see here very nicely, induces, this supernatants induce the IL-10 receptor. The loss of this indole results in a very minimal induction of the IL-10 receptor. So again, suggesting that indoles generated into the supernatant of bacteria probably signal to the epithelium to drive an anti-inflammatory response.
So you seem to show that the kind of the butyrate produced by the microbiota is important for kind of mediating this disease. Is there any indication that there's like predisposition for certain microbiomes that don't produce as much butyrate that are then more conducive to getting this colitis?
Right. So chicken and egg story, right?
Yeah.
Right. Most studies are suggesting that I don't think that there's a susceptible microbiota. Probably looks to be more inflammation-driven depletion of these microorganisms. So the microorganisms are primarily type 4 Clostridia, are the big, really big producers. They appear to be, for whatever reason, we're not sure yet, they appear to be very susceptible to an inflammatory microbiome. So generation of the inflamed microbiome appears to be depleted of those, particularly those Clostridia. Well, we don't know why. I will admit that we don't know what the basis of that depletion.
So I'm curious about basically the life history of tryptophan sitting in the intestine. So at one point I thought I had heard in old biochemistry classes that he actually did go through serotonin to get down some of these pathways. So in the life history of tryptophan, what percentages are going in which directions, and how does that change? Where's the balance go?
Right. So in a healthy colon, for example, 90% of the tryptophan is generated locally metabolized to serotonin and ultimately histamine. In the inflamed tissue, 90% goes toward kynurenine. It's really interesting. So the primary enzyme that generates kynurenine is IDO1, and IDO is gamma interferon inducible. So during the active inflammation, essentially all of the tryptophan that comes in through cells is used to generate kynurenine. On the microbiota side, it's, believe it or not, still not quite understood why indoles are made. It's thought to be probably a communication between the microbiome, so they probably interact. Probably something similar to what we see with quorum sensing, because it's a way of bacteria interacting.
And that goes from 0 to 90, or that goes from 0 to?
Well, there's sort of a steady state production of indoles by your microbiota. For the most part, we have not seen that those change during inflammation. If we look, for example, at indole in stool samples, so we don't really see that those change per se. What penetrates the tissue probably does change, and probably related to barrier. Probably changes in barrier result in increased access of indoles. We think that's probably anti-inflammatory pathway. So it's an adaptive pathway that the host is used to utilize, probably to decrease bystander damage associated with it. That's at least what. Yes, in the back.
So in the inflamed gut microenvironment, does the physiological hypoxia correlate with increase of alternative terminal icon receptors, or does that select for primarily anaerobic bacteria?
Right, so that's a good question. So shortly after our paper came out, there was another paper that came out from a group in California that suggested that in fact during inflammation, during active inflammation, you actually increase the amount of oxygen that can be made available at the very luminal surface. That actually results in the blooming of an aerobic bacteria. So, in particular, aerobacteriaceae that are facultative anaerobes, facultative aerobes. These, essentially the availability of oxygen makes those, essentially drives that blooming bacteria. So, you're probably, in fact, depleting at least in the local environment, you're probably depleting the air, which could explain some of the changes that we're seeing with you. Good question. Okay, thanks very much.